Yeah, welcome all to another session, weekly algo session from SDE Skills. And today we'll be discussing another 3 to 4 patterns of the remaining DP from Geeks for Geeks. So the first pattern is, I think, about the climbing or the climbing staircase, similar to that, right? It's a counting number of ways you can count. So that will be done by Shashank. So we have divided into 3 to 4 problems. One will be presented by Shashank. And second is the, I think it's the partition problem. And that problem will be presented by Safal. And third is about coin change. Leon will be presenting that. And I'll be presenting the integer break in case if you find time. Okay.
Yeah.
So let us go with Shashank.
Yeah, sure. So then let me start the first one. So it's a very common problem, like most of you might have gone through. This is the problem that I'm taking. Like count the number of ways to cover a distance. So it's like a distance is given, and you have to count the number of ways to cover the distance with either one step, two step, or three step, right? So it's like, I mean, staircase is here, let's say, right? So and you are at this position. So either you can take single step and reach at this point, or you can take two steps and then single step, or single step and then two step, or directly a three step you can take, right? These are the, like, what do you say, the rules what they have defined. So if we draw the tree diagram, let's say I'm trying to come from top to down. So if I could have reached n by doing n minus one, like single step, or I could have done two steps, or I could have gone through n minus three steps. And if we boil down further, again, what you can do, n minus two you will have, then n minus three, and n minus four, right? Like, I mean, for reaching this, either you can take one step, or you can take two step, or you can take three steps. Similarly,
It
yeah,
will be n by n minus 1 again, right? In this case. Yeah.
yeah.
Yeah. Instead of n minus 4. Yeah.
Okay, this one, right?
Yeah. Yeah.
Yeah. No, I'm saying if we are at this step, and if we take the one three step bump, then we'll reach to this. I mean, n minus four plus three.
Oh, yeah. Sorry. Yeah.
Yeah.
That's right.
So you can observe, like, these are the repeating problems, right? N minus two, and this n minus three. And if you draw it more further, what will happen? N minus four, you'll have n minus five, like this is for one step, this is for two step, and this is for n minus six, three step if you take. So these are the overlapping sub problems that we see, right?
Correct. Yeah.
So, so it's straightforward. Like, if you can write define a function for this, you have to reach nth step. So it will be the number of ways of reaching n minus one plus the number of ways of reaching via n minus two, and the number of ways for reaching n minus three. This is the recurrence relation for it. It's more of a, you can say, Fibonacci, right? Not Fibonacci, but Trifonecci, we say something like that. Three series. Yeah.
Similar to that, right?
Yeah. And couple of base cases, like if you have zero steps, then it will be zero only, right? No steps are there, so nothing. So for f of 0, you'll have 0. And coming to f of 1, if you have to reach one step, so there is only one way, like one step only you can take. And even for f of 2 also, because this will start only from n greater than equals to 3. This equation will be valid only for greater than equals to 3. So f of 1, f of 2. So if there are two steps, so there will be only two ways. Either like one step you can take one way that, or you can directly take a two step, right? So f of 2 will be your 2. and f of 3 also we have to calculate, right? So that also manually we can do. So f of 3 will be what? If we yeah, f of 3 will be again this. You have to reach here, right? So one step this. I mean, if you take single step, so this is one way, and if you take 2 and then 1, and again 1 and then 2, so that will be 2, and 1 directly 3. So total number of 4. So f of 3 will be 4. And now from 4 onwards, you can use that formula like if n greater than equals to 3. I mean, not equals to, greater than 3. We can use this f of n is n minus 1 plus n minus 2, and this is n minus 3. Right.
Okay, yeah.
So any doubt in this, or I mean, it's more of a Fibonacci kind of, like only we have to take care of the base cases.
Yeah. So you're trying to say that we have an overlapping sub problem, and also we have a optimal substructure as you have shown over here, right?
Yeah.
So this is
And
a
there
very big problem.
yeah.
You can solve with the top-down approach or the bottom-up. Yeah. Yeah, makes sense.
This is the same problem only, but here just they have taken it, what do you say, 1 or 2 steps.
Right. Yeah.
So if you have, I mean, I'm showing you first the, what do you say, the top down. So this is your base case. I mean, if distance is negative, you'll return 0. And if it is 0, distance is 0, then return 1. I think it should be 0, right? It depends on what, like.
Yeah, it should be 1. Because look at on line 31, you sum them up, right? Because if you return 0 right there,
Okay.
and on line 31, that's gonna be 0 plus 0 plus 0, gonna be all 0.
Okay, yeah.
So base
Right,
case will be 1. Yeah.
Distance minus 1 at one point have to go back to 0.
Oh,
So,
but logically looks like if the distance itself is 0, why it should be 1?
oh, one way, I say one way, not 0.
Yeah.
You know, one way to get to
0 distance.
Yeah, to stay where you are is one.
Yeah, that's the basic case. Yeah. So if you don't have any steps and you still want to attain a distance 0, you can do that with one way, right?
Yeah, stand
That is
there
the way you
itself.
have to look at it. Yeah. So that is the base case for this one. Yeah. Makes sense.
Yeah, you have to set it that way so that you know the on line 31 that makes sense.
Yep.
Right.
Yep.
The main. I mean, that's the main reason.
And remaining like that number of ways of that, what is it, these 3 recurrence relation or equation.
Yeah.
Yeah. So this base case is very important.
Yeah.
Yeah. So that base case actually, the way Leon was saying, if you look from line 31 to 32, we are not adding any numbers, right? So the number what we are adding, we get it from line 27, and that is what the base case. And yeah, or else then you will have to add 1 1 1 everywhere, right?
Exactly.
But this is also one way to do it. If you look at the base case as this one, okay, we have 0 steps and we have to add in 0 distance. So at least you can do it in one way, and then we can justify that base case and then implement this way.
Yeah, done.
Makes sense. Yeah.
And coming to bottom up, so it's 1D array. I mean, what you can see like this only you can. So let's take in for 4 steps only. So 0, 1, 2, 3, and then 4. So a base, I mean, here I'm taking, but for 0, I'm taking as 0 in bottom up. And for one step, it will be 1 only. And for 2, I'm taking as 2. And now for 3 will be the sum of these 2. That is 3. And for 4, the sum of these 2 will be 5. When I'm returning this value. So it depends, right? Base case. I mean, I mean, sometimes it changes. Like in top down, we are saying that for 0 they are taking as 1, depending on the way the recurrence relation we are written, right?
Yeah, so we can implement that in a different way also. But the
Yeah.
way we are implementing, we can use that base case. But for this bottom up, yeah, this also makes sense. So we'll have to be careful on how we are selecting the base case, right? For both of them, the approach it will be different base case. Yeah.
So this is like more of a Fibonacci. I mean, this is exact Fibonacci only.
Yeah, this one is the climbing stairs, which has only two steps to climb. It is almost that. But that was a variation of this Fibonacci or maybe the climbing stairs, right? So
Yes.
you might be asked questions in different ways. So that is a different flavor, right?
Yeah.
And it can be more also, right? So if imagine we are asked instead of three, more than three, like four, so how do we do that? Uh, so that will be a really that example is a good way to understand and expand our thought process, right?
Yeah.
So we can further. Can you? We can further the optimize on the space complexity, right? If we think of like in terms of window, let's say, because we need only two steps. Or let's make it generalize it. You can do in k step. And then we don't need. We may not need an array of n element. We only need an array of k element, right? Because at most we go back only like k,
Steps.
right?
Yeah.
K step. So that probably we can optimize on the space. I see a lot of problems similar like this. We can optimize on space potentially, but I don't see a lot of people don't optimize on it.
Yeah,
And for 2, you can use 2 variables also will work.
yeah, that's what
Yeah.
exactly he's trying to say.
Yeah.
Yeah. So in case if we are given a problem instead of two steps, one and two, if we're going three, so we can use a variable of three variables, or we can use an array of k size, which will be the
Yeah.
number of steps, right? So yeah, that's good one. So we can optimize on space. Absolutely. Yeah. Yeah.
Yeah.
That's good.
So any doubt? Yeah.
Yeah. This was an easy problem as per the lead code, but I don't know. It is really easy because if you go for number of steps more, then it might be slightly difficult to understand if you just come across this problem, right?
Yeah. I mean, in what sense, like just
Yeah, if you are given something like this, and
yeah.
then it's it is yeah, when you try to analyze it carefully and you just take a deep breath and understand, then it relates to that problem, Fibonacci series problem, but
Exactly.
it's not very evident immediately if you look at the problem statement, right?
Yeah.
So just do a more thoughtful, because when if it someone says if we have four steps, then you just start thinking in different direction altogether. Yeah,
In that case.
yeah. But if you just try to understand it is similar an extension of a Fibonacci series or this climbing staircase, then it is more easier to implement.
In
And the
makes sense.
implementation, the geeks for geeks are almost the same what you showed, right?
Yeah, almost.
Okay. Okay. Yeah.
Same there.
Right. Right.
Yeah. Then we can move to next. Or if
Okay.
any doubt.
If you have any questions on this problem, sorry, my mic is back. Yeah, let's move to the next one. Yeah.
Shuffle, you're ready?
Yeah,
Or
yeah.
Leon? Okay, go ahead.
I'll do it. Yeah. Hello everyone. My name is Safal. Today I'm going to talk about partition problem of the dynamic programming concept. I have few slides, so we'll look at few slides first, and then we'll dive into a lead code problem that relates to that partition problem type. So let me share my screen first. All right. Which screen are
Right.
you guys are seeing? This one, right? The
Yeah, the
one with
dynamic programming partition
okay,
problem. Yeah.
okay. All right. So partition problem, it is one of the problem type under the concept dynamic programming. And what we'll basically do on my session is we'll cover briefly what is dynamic programming, right? And we'll talk about the partition type problem. We'll review a problem on this topic, and that problem is basically the lead code number 416, which is partition equal subset sum. We will look at key observation on the problem before we dive into the problem, right? We'll discuss solution. We'll discuss the two solutions. First, non-efficient way, recursive solution, and then we'll look at the efficient way, dynamic programming solution, and then we'll go for the feedback. All right. So what is dynamic programming? Basically, it's the concept of solving a complex problem, right, by breaking into small sub-problems. And when you do that, sometimes, matter of fact, a lot of times they have overlapping, sub-problems. And what does that mean is basically we have subproblem that's calculating the result again and again, and we don't and we want to save our compute power, right? So basically what we do is we store the results of the subproblems to avoid solving the same subproblems multiple times. And this concept we'll usually do it using two techniques, memoization and recursion, but this process, this concept, that's what dynamic programming is. Okay. Now, partition type problem is one of the problem type that falls under dynamic programming, right? And the example of that problem will be something like this. It'll say, hey, determine whether a given set on an array can be partitioned, right? So basically what it's asking is, can you convert your array into two sub-arrays, n, and there is n word. So it has to satisfy two conditions, and the sum of the elements in both subarrays should be the same. For example, so if we look at our array 151, 115, it satisfies the above two condition. Why? Because um, the array can be partitioned as 2, 1, 5, 5, and 11, and both of the sum is 11. So we can say that, hey, I can say confidently that this array I can partition into two subsets. Now let's review our practice problem question. So on our practice problem, we're asked, given a non-empty array nums containing only positive integers, keyword positive integers, find if the array can be partitioned into two subsets such that the sum of the elements in both subsets is equal. Same concept as above, right? Um, and I put in the numbers the same too to make it easy. So basic same thing, 1, 5, 11, 5, true, and we have to prove that why is it true, right? Um, Now, key observation after we look at this question that we can make on this question, and those observation are three observations that I noticed. Now, to divide the nums array into two parts so that the sum are equal, right? That's the key part. So we need to make sure that both subarrays, the sum are equal. Sum of each subarray should be sum by two, right? So on our example, let's see, 1, 5, 11, 5. Our total sum is 1 plus 5 plus 11 plus 5, which is 22, which means the sum of each subarray should be sum by 2, should be 11. Then only it can be 11 plus 11, 22. That's one observation, right? So sum of each subarray should be basically half. Second observation is sum should always be even. So this one's a little confusing. So basically what does it means is, so on our point one, we basically said, all right, so if I give a value x to one of my sum for one of my subarray, then x plus x should be the total sum of the array, isn't it? So that's what I said here. So which means 2x should be the sum of the total array. Now, if now on our problem it says x can be x is a positive integer, right? So a positive integer, multiplied by 2 will always gives us an even result, right? That's just a math fact. So x, remember, the sum of subarray can be odd or even, but 2x will always be even. So that's why the observation was sum should always be even. Third observation is, now once we have an array whose sum is even, if we find a subarray of the elements whose sum is sum by 2, then the rest of the elements will also have the sum of sum by 2. What does this mean is, so if you look at this array, right? So if if I just go and find not necessarily 22 but 11, if I just go and find any subarray that has a sum of 11, so which would be uh, 1, 5, and 5, the rest of the subarray should also equal 11 because you know to make it to be partitioned equally, it'll be 11 plus 11, 22, right? So basically, once we find a subarray of 11, the another has to be 11. So based on these three observations, we'll go and review the same problem on the lead code. Okay, so let's go to lead code and view those two approaches I discussed earlier. Now, the first approach I took, this is the recursive approach, right? You guys are still seeing the lead code and my little tree, right, on the right?
Right,
Yes.
right. Yeah.
Okay, so this is the non-efficient way, I would say, okay? Um, all right, so what's happening here is I have a can partition method, right? And I have the helper method. Now, can partition method is basically prepare. Remember on that example where we had, let me actually pull on this example too. Okay, so on that example, can is actually preparing this so we can send us we can send the subarray to check if can be basically what it's doing is we'll go line by line, right? If none is null, numb's at length, then we don't need to worry about it, just return false, right? Otherwise, let's say my sum is 0 for now and give me the sum. So basically it says give me 22 and check if it's even, right? That was the key point. If it's check check if it's even. If it's not even, return false, because based on our observation, we say only even. Only even the sum has to be even, right? Now, and now once we find out it's an even, then what we're doing, all right, so let's cut it into half. So 22 was cut into 11. Now let's send this. So it's, I said 11 as my target, right? So now send this sum to our helper method. Now helper method will do the recursive call stack to solve this problem. So now what this helper method does is now what we're basically doing on this is now if you look at our tree on the right side, so we are using, remember this is OR function, right? OR operator. So we're basically taking, right? So for 1, 5, 11, 5, we're basically taking uh, whether to, so we'll look from the back, right? So 1, 5, 11, 5. We're basically saying whether to include my 5 in my solution or not include my 5, whether to include my 11 or not include my 11 in 5, and so on. So basically for every element in this array is checking whether I should include it or not include it or not include it. So based on this observation, I made a little tree and how this code was running. And it on every on every recursive call stack, if you notice, so it goes uh, first of all it goes depth, so it goes all the way down to 1, and then it checks on each call stack should I it does nums and subtracts the last element, 5, and then it checks, okay, so if I just do 1 5 1, all right, does that equal to my target 11? No. So and then okay, if then I'm gonna drop the 11, and what does that result come out? 5 1. So basically it's include not include. So the reason this efficient is not efficient is, now if you notice, for every element I have to check, okay, include and not include. So that's exponential, right? So if I say n is the number of elements, then that's 2 to the power n. Now this solution tries two possibilities with including for every element. So this is just not a feasible solution, right? For even for a small like a size array for a size of 4, I have like this tree, imagine for like a lot of numbers, that's why we had to come with an efficient approach. Now if you want to also notice is that a lot of the here are a lot of sub problems, right? It's computing the same number, so we have to be able to find a way to store that solution for that sub problem. So that's why we come up with dynamic programming. Now dynamic programming, what essentially what we do is our earlier condition is still the same, right? Num star length sum, it's essentially doing the same thing. It's giving me the sum, it's checking if it's even or odd. If it's odd, returning false, then it's sum by 2. Now here where the logic starts. So it's gonna basically create, instead of going through this recursive call stack to find out the answer, it's gonna make a 2D array of Boolean first, right? And then it will try to it will store the result on this 2D array. Now, on this 2D array, first what it once it creates this Boolean 2D array, what it does is, okay, so for my, so let's look at the array 2D array first, right? So I made 2D array row and column, right? So rows 1, 5, 11, 5. Now these are the elements of my array, right? And I put in extra elements. So basically it's a size of 1, 2, 3, 4, 5. And my sum, which look at the sum. So sum is target is 11, right? So, and I put in extra column in there. So basically these are the sum 0, 1, 2, 3, 4, 5, 6, 7, and 19, 11. Some of the elements in the array from 0 to 11 and a number of elements in the array, right? So now I put in, okay, my first column is all true. Why? Because we can always make up a sum of 0. So basically it's saying, okay, so what it's saying is, okay, sum is 0. Do you have an element that can sum up to 0? It's saying, okay, well, in order to make a sum of 0, we don't need any animals. So we can just say, okay, we can make a sum of 0 with an empty array. So we just did true, 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 right? That's what this for loop is doing. Now the second for loop, what is it doing is it essentially, it has two concepts, right? So yeah, okay, so it starts with the uh, row 1, right? And it starts with column 1. So this is where the operation begins, right? And uh, the whole, now then it does if else check. Now what this, in plain English, what this if is checking is, all right, so if my column number sum, and this is what this particular logic is doing, but I'll explain it over here. So it says if my column number sum is less than the element value, so the column number sum in this case is 1, it's less than the element value, uh, 1. If 1 is less than 1, uh, is look at the value at the top, right? So is 1 is less than 1? No, then it goes to the else block. Now what this else block is doing is otherwise get the top value, right? This is what it's doing. This is saying get the top value. So it'll point here and use an OR operator used right here, right? From the top value, move the corresponding number of steps back and return the value. So what this means is, okay, so from here, return, when I say corresponding number of steps, it says return, if we do this calculation, it'll say return, push back 1 time. So go up 1. What is it? True. That's why it says true, right? That's what it's doing. So it's a little harder to visualize, but once we figure out this table, once we get the numbers going, basically if it's checking if my column number sum is less than the element value, else is checking get the top value or use an OR operator from the top value, move the corresponding number of steps back and return the value. Now remember, the logic is still the same. Logic hasn't changed, right? So if we look at our earlier problem, we were still doing OR, right? So we were including or excluding, right? Here, instead of just going through all this 2 of n recursive call stack, what we're actually doing is we're storing the values in our DP table and using our just OR table, using the values from a DP table this is much more efficient, right? And essentially our goal is, so let's look at a few things. We're not going to go over all the table, but we're just going to go a few rows just to make our understanding clear. Okay, so now our sum is 2, right? And can I make a sum of 2 with the 1 element? No, that's why it says false, right? And it also goes over, so using this if else block, it's just the same logic, right? So let's look at here. So basically it says, okay, if I can make a sum of 2, I can't make a sum of 3, 4, so everything is false, right? Let's go to this 0, 1, 2, third row, right? So at this point, I have 2 elements, 1 and 5, and I need to make a sum of 1. So can I make a sum of 1 using the elements 1 and 5? Yes, because we have 1 element, which is 1, so we can easily do 1. And this is what the if else logic does as well, right? So can I make a sum of 2 with the 1 and 5? Nope, because we only have 1 and 5. Let's look at number 5. It says, can I make a sum of 5 using elements 1 and 5? Now it says true. Basically, it uses the same logic and else block. It goes go up and subtract 5 times. 1, 2, 3, 4, 5, right? Now, similarly, using the same logic, it builds the entire table. Now, the key observation here is ours. We want to see. Remember what is it returning? It's actually returning this value right here. That's the only value we're interested on, right? So basically, here is saying, can I make a sum of 11 using my elements 1, 5, 11, 5? And if you look, it says, all right. Using this logic, okay, go up and 11 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's why it's true, right? So that's how the solution comes out to true. Now, time complexity wise, now instead of going to our other solution, which is 2 of n, we're essentially doing the same thing. We're using DP table. Now our time complexity is actually O of a number of elements in our rows. Now, rows, what was our rows? Our rows was the number of elements in the array, right? Multiply by sum of the elements in the array from 0 to 11. So it is much more efficient. Let's see. Yep, that is it for me. Let me know if you guys have any questions, feedbacks, or anything. Thank you.
Yeah. So yeah, this was very good, neatly explained. Absolutely, it's nice. Yeah.
Yeah.
I think
Like,
one thing is missing
Nice.
that when he's telling he's going, I mean, when the number is greater than that, he's taking the value from the up. So what is the inference out of that? I mean, he's not taking that number, right?
yeah, so knapsack, right? Knapsack
Yeah,
approach, right?
that part was, I mean, missing a little bit.
Right, on the you mentioned on the if block, correct? Right here.
Yeah, else part.
So basically, if my sum is less than the element value, look at the value of the top, but basically it's saying exclude that value.
Yeah, so that point you'll have to. Yeah.
Okay, got it.
Yeah. And also to add to what Safil said, like it is very important that the numbers are positive, right? Because if they're negative, then we can have a negative sum, which we cannot represent on a 2D index, like the index of the array. So yeah, it's important to have positive numbers only, right?
Exactly.
Right. Yep.
Yeah.
That's awesome.
Positive integers.
Yeah, it's good. Like you came up with all the key observations before presenting the problem, so it made very easy for us to go through. And secondly, when you said the non-efficient way, that is right, but you came up with the implementation of a very difficult problem like the bottom-up approach, and that's really good. Yeah, but usually what we also do when you say the non-efficient one, which was the recursive way, so we can slightly tweak that implementation itself, and use memoization and then make it almost the time complexity wise the way we are doing for the bottom-up approach. Yeah.
Right.
Yeah.
Yep, we can also do that.
Yeah.
Yep.
Oh, that's a backtracking only, right? If we prune it, we can pass that solution. I'm not sure. The one Safal was mentioning using the tree.
Oh, this one actually goes out of induction, I think. Yeah. Time limit exceeded. Yeah.
Yeah, it will, because it's exponential.
Yeah.
But that's very good way of bringing both of the solutions and showing how the bottom up in this case is more efficient than the recursion one.
Right.
Yeah, that's good.
All right. I'm gonna stop my share. Thank you, guys.
Any questions on
Thank
this?
you. Good key observation. It
That was
helps to
very good
retain
actually to come up with
information for a long time.
Thank you.
Right.
Yep.
Yeah. Okay. So Leon, would you
Let me
like to
share
go
my
through?
screen. Okay. Ooh. Okay. You can see my screen, right?
Yes.
Okay. So so today we talk about three. So far we talk about two dynamic programming pattern. The first pattern that Shashank doing was to count the number of ways. Okay, and then the second pattern that Saffold was doing was like to count, you see the number partition and return like true or false. And I'm doing the coin change. This is also a classic problem. This is like the category of this DP is like minimize and maximize. Okay, so the problem is you are given coin of different denomination and the total amount of money, and we need to write a function to compute the fewest number of coins that need to make up to that amount. If the amount of money cannot be made up by any combination of the coins, to return -1. Okay, so we might assume that we have infinite number of each coin. So the key to see this is the minimize or optimize DP. Is we see the few number of coins right here. Let's see. Okay. So we try to. Why I cannot draw?
You want to annotate?
Yeah.
You'll have to click on the screen, and the top you'll see view options. Then you just click on that. You see an annotate button there.
I don't see it here, but
it's not there. Okay, then I think yeah, you can use new OneNote.
See, I tried to draw it here, but I.
OneNote, you'll have to select a pen, and then you'll have to select a pencil, and then assign the
drawing mode.
Yeah, on the top, whatever the pens you see, you select it.
Because I'm sharing my screen, right? Let me see. Sorry. Well, maybe I just stop sharing for now.
Sure.
And then, sorry. See. I cannot see.
We can see your lead code screen now.
Yeah, but I try to draw something. I'm unable to. I don't see like the pen like when I'm on Zoom.
Yeah. I also can't see. I think it's
okay.
I also can't see.
Oh, so is it because they are not the host? So can you make him a co-host, Shashank?
Yeah, sure.
Yeah.
Leon is not which. Okay. No, I am also the co-host only. I think Bhavesh can.
Bhavesh, can you please make Leon?
Yes, I just did. Yeah, I just
Yeah,
did.
he did. Yeah.
Mm.
Can you try it again, Leon? Maybe you'll have to unshare this again.
Still, it's not there. I think.
See, we don't see it, right?
Yeah. I don't know what's it.
Okay, maybe there's some, yeah. So in this case, if you just click on any of the pencil, yeah, and then you will see all the shapes, right? You will have to select, yeah.
So you click on the pen, right? And
yeah, the pen, and then it will give you an options. You select the pencil, and then you select any of the colors, and then you just come out and should be able to draw.
Oh, okay. Yeah. Oh, I can see it. Okay. So where's my eraser? Oh yeah. Okay. So we have the coin, right? So for example, we have a denominator, you know, the coin denominator of like what might be
125.
yeah, 1, 2, 5. Then we want to make say we want to make like the amount 11, for example, right? So like we can draw a decision tree to determine like the number of minimum coin we you know we number of coins to make up to 11. So for in here we can make like if we pick one, then we still like have the number of coins still 1, 2, 5, and then if we pick one, then the amount going down to 10, and if we pick you know we pick 2, so the number of coins still the same, and the amount gonna go into 9, right? And then we can make that branches, different branches for this different amount, right? Until like we find until like the amount become 0. If the amount goes down to 0, right, amount going down to 0, then we can return 1. I mean, we can return 0 there. Yeah. So basically, like we need to iterate through all the for each of the coin, we have to iterate through that and to find like the number of, let's see, yeah. So we have to find the number of minimum coin to change. So we have like a function f, maybe fn equal mean, you know, minimum of oh wait. Of f n minus, in this case, -1, right? And then f n minus 2, and then f n minus 5. Okay, plus 1, right? So we think about, let me see what they say. Think about at this point right here. If we are here, here's the current amount, okay? Here, let's say suppose here's a current amount, and then we want to find the minimum of coin to get to here. What we need to do is to find like, okay, what is the minimum amount to, you know, for for the current amounts, subtract 1, right? And then what the minimum for the current amount, subtract 2, and then minimum, you know, for the current amount, get subtract 5, and then we get the minimum out of those, and plus 1. right? Because that we need one more coin to get this to this amount right here. Okay, so is there any question?
So you are saying that the place where you're showing this arrow, so
Yeah.
if that is an ith index, and then you're saying that you can go, in this case, we have a coins with denomination 1 to 5. So I first go from I backwards to by one position. So
Yeah.
whatever the value is there, okay, and also I can go backwards by 2 positions from I.
Right.
So I minus 2, and whatever the value is over there, and the similar thing I do for the 5, right?
Yeah.
So whatever is the minimum value of all of these locations plus 1 will be the one value which you will be assigning to this ith location, right?
Yeah.
Okay.
So that means that at this position right here, that would be the minimum number of coin to get there, right?
Right.
That's a recursion equation. Okay, so that's this top-down approach. Okay, so let me share my code.
Sense. Yeah.
Okay, you can see my code, right?
Yeah.
So this one, like this is the top-down approach. I have it right here. That I'm using the helper for the recursion. So we pass in the coin and the amount, right? And then I have to create a max. Like the max is my my like number of way to the maximum number of way to for the to change the coin. This max is like an invalid one, right? I have to mark with something like invalid, right? So I use the upper bound to mark it. This is invalid number for.
But I was thinking, like, if you just have coins of only single denomination 1, right? So then max equals to amount will be a valid one, but you are adding more 1 to that, so that is the reason it is invalid, right? Okay.
Yeah.
Okay.
Yeah.
Excellent.
So I make it for the invalid one. Then just ignore the memo for now because that will be. So I just go in and then call my helper function, pass in the coin and the amount, the max, and probably I pass in a memo too. The memo will be initialized with the amount plus 1 and initialize with the max value with all the invalid value. I pass it in. And then when it's done, then they return the result. If the result is greater than the amount, that means if it's greater than the amount, that means that's the invalid one, right? So I return it -1. Otherwise, I return the result. So here in the coin change helper, it do the recursive call. So when the amount, because we remember we keep subtracting, the coin from the current amount. So the amount gonna go down, up to the point. If the amount equal to 0, then I return 0 because that, like the number of way to get to the minimum number of coin chain to get to that zero amount is 0. So I return 0 there. And then
so that is a base case.
Yeah, that's a base case there. Another base case is like if I overshoot, I mean, if the amount is less than 0, then I return the invalid one. Max is an invalid value result. So here I say, if I already have processed the result, if I have not processed the result yet, right? That means max, I initialize the max, the memo with the max right here, the invalid one right here. So if I have not processed it yet, then I go in and find to process and find the minimum number of ways to get to the amount, right? And when I go in here in line 19, I initialize the result to be the invalid one. I should rename this one invalid result. And then I look through the number of coin, right? And see if this if the current amount is greater than or equal to the value of the coin, right? If it's greater than, then I can get the, I can get the result. The result will be equal to my current result, which initialize to the invalid, and then recursively call the helper function. Have to pass in the coin, and the amount. Now the amount will be equal the amount, right? The amount subtract the value of the current coin, right? That means the amount keep going down.
So that's the remaining amount now, right?
Yeah, that's the remaining one. Yeah, and then the helper function will return me the minimum amount to get to that coin value right here, right? Then that's why if I want to include the current coin, I have to add 1 to it. That's why I add 1 to here. Okay, so whatever the minimum, then that will gonna return at the result. Okay, and in here the result, I will have to check that if the result equal the max, I want to add 1 to the result, right? Because if I add 1 to the result, that means I'm already processed this amount, right? So if I add 1 to the result, that shows that up here, I already processed this amount. Next time, if I go back here, I'm not going to process it again. Okay.
So you are exceeding the amount, right? In that case.
Yeah. Yeah. Because if I don't do it, if I don't do it right here, then the memo amount will be the same as the max, right? And then next time I come here, it's gonna redo this again. Yeah, so that's why I have to add 1 to it. Okay, and finally I return the result. Okay, so this is a top-down approach. Anybody have any question?
Well, yeah. So this is So only the different thing what you are using in the memo, you are actually initializing all the memo values with the max value. That is a very different way of doing it, because usually whenever I do, I always initialize to -1. Yeah. But this also makes sense, right? Yeah.
Which one you use?
The memo part actually on line 6, when you are initializing to max. So yeah, that's a different way of doing, only a different thought process. I'm just
so
trying
you
to
use
understand.
-1?
Yeah, I usually use -1, but yeah, you can use this one. Yeah.
Yeah. then how do you get the minimum? How you handle the minimum? Because that's gonna be minimum of -1. They're gonna pick -1, right?
Right. I don't go in that statement. Before that itself, I just check if it is -1, and then I, if it is -1, if it is not -1, then I return my memo. Okay. Or if it is -1, I actually go and do the for loop complete, and at the end, actually, I assign the memo value. So the way you are doing on line 24. So almost the implementation remains same, but I'm saying it's a different way of thinking. Yeah, and that's good.
Okay. Okay, that is the top-down approach, and here's the bottom-up.
And only
approach.
one thing, this one, the pattern what you are explaining and Safal's pattern, they are slightly similar, right? Because on the line 21, you are comparing the amount to be greater than or equal to coins I, and in his case, he was just looking for the value greater than. But there he was using a Boolean variable, and here you are using a minimum of the two values, right? Just
right.
to compare those two patterns. But yeah, but there are lot of differences if we just tweak the pattern, and then we can get solve different ways of different problems of dynamic programming, right?
Yeah. And the reason that, the reason I use on line 21 because I want to make sure the index is not I try to make it that not go negative, right?
Okay.
Because otherwise amount minus coin would be a negative value, right?
Yeah.
So maybe I might not need this if condition on line 15.
Because minimum,
but yeah. Okay, so you're saying that if we are using that, that might be a redundant.
Yeah.
Yeah, but usually we keep those things. Yeah, okay. That is what it naturally comes. But you are taking care of it on line 21. Yeah, that also makes sense. Yeah. No problem. Yeah, this is also good.
And yeah, I think it's similar to the way that Shashank does, but the difference is this one, Shashank does the count, the number of way, right? It's just adding, and here I have to do, minimize or optimize. So I have it here.
Yeah.
So this is the bottom-up approach. So on line 30, I just create the max is the amount plus 1. Then I create the DP array or vector, and all initialize to the invalid value, which is max right here. And then on line 32, I set the DP 0 to 0 because there's the number of minimum way to change, amount 0 is 0, right?
Okay, right.
And here, I just started from the amount, the outer loop, the amount from 1 to I equal 1 to I less than equal amount, right? That's the outer loop. And in the loop, I loop through each coin, right? And here I say if the amount, the current amount, I's current amount is greater than or equal the value of the coin, then I update the DP, right? DPI would be equal minimum of DPI, or like, DP of I, the current value, minus the coin, the current amount, I is the current amount, minus the coin value, right? And then plus 1 if I pick this coin, then I have to plus 1 to it.
Yeah.
Okay. And then finally, I return the result. If the amount is greater than or equal max, then I return -1. That means this one is, it's invalid way. There's no way to get to, that amount. You change, you get coin change to that amount, then I return -1.
Yeah.
Otherwise, I return the result.
So you're almost converting the bottom up into top down, right? It seems to be almost like that, but it's not, right?
Yeah.
Following the same pattern, at least the for loops, and when you are assigning the DP values, you are using the minimum and then going to that previous row.
Yeah.
And it's more easier to understand this way also, right? When we
Yeah,
do
because like if you add this, for example, you add this amount, then you can get the minimum. What would be the minimum of coin change to this value, right? The current value minus the coin value, right? That minimum, then when you get it, you +1 to it. You pick the current coin.
Right. So
That's
the
why
way you were describing on that graph also initially, so that is exactly the way the representation is. Yeah, sorry, Sujan, go ahead.
No, same thing. He's including, that's why he's subtracting the amount from I minus coins of J plus. Knapsack way he's going, either he's including or he's not including, right? So DP of I is not including and DP of I minus coins of I is including. So he's subtracting that amount, that coin denomination, and then adding +1.
Yeah, that's right.
Yeah. So I have another method because I was, for this problem, I'm curious if we can change the order of the nested for loop, right? So if we make like here, we make number 34 as the outer loop, and then number 33 is in the loop, and see if it's still working. And that's why, I do it right here. And
does it work?
Yeah.
Okay.
When I change it, and the result, still come out correctly. And one key, I observe on this is it only works because I'm doing the minimum, the minimize, or can it work and they do the maximize. Because
go ahead.
Because if with the minimum, you always pick the minimum one, right? Regardless of the order. So, I cannot draw right here, but so for example, with the minimum, if I want to get to 3, right? Let's say the amount equal 3, right? Then I can get to the amount 3 by either pick the first coin to be 1 and the second coin to be 2, right? Or I can pick the first coin 2, the second coin is 1, right? So at this position 3 right here, at amount 3, it doesn't matter, what combination I pick, because if 1 plus 2 equal, that's 2 coin change, right? And 2 plus 1 is also 2 coin change, right? So it doesn't matter what order I pick.
The values of the coins don't matter, you mean to say. Okay.
Yeah. Okay. But let's say there was a problem, the coin chain problem too. Let's say like you count the number of ways. It's the similar problem, but say you count the number of ways to make the change of 3, right? Of given, let's say you count the number of ways to make for this given amount, right? So then you have to count them differently, because if you count the way like like for example, we count the way like Shashan did, then we're gonna have 2 ways to do it for number of coin change. This is one way, and here's another way. Then we will count double, right?
For different ways, okay.
Yeah.
Permutations, really.
Yeah. So to make, if we want to make that, like, if we want to avoid counting double, we don't want to count double, then we have to use this one. This method right here. We have to put the outer loop had to be the coin.
So that's
range.
the only difference if we make, and the coin to problem also works. Okay.
So if we want to make it unique, then like count, 2, there's only one way to make that, we don't avoid duplicate, then we have to use this one. But if we want them to count duplicate, then we use the other one. And the other one, you can see why, because let's say I'm at 3 right now, right? I can, if my current value is 3 right now, then the number of ways I can count 3 is 1 plus 2 and 2 plus 1. Right? Yeah. But if you want to remove the duplicate, avoid duplicate, then this the outer loop would be 57, because we think about on line 57, we say that, let's say we already processed coin 1, we done with it, and coin 1 already considered. Now, we go into coin 2, and we say, okay, now consider coin 2 only, right? That's how we can remove the duplicate then. Versus on this one, we're gonna consider both. For each amount, we're gonna consider both coin 1 and coin 2, and, again and again at every amount, right?
Right. So with just a small tweak, we can actually solve a different problem.
Yeah.
That's
but we also see why, for minimize problem, this, when I change the for loop, the order for loop, it doesn't matter. It still, give the same result.
Yeah.
Because we pick the minimum one, it doesn't matter, 1 plus 2 or 2 plus 1, that's still the same, the amount, that's still 2 coin changing.
Yeah. That's good.
Okay. That's all I have for this one. Thank you, guys.
Yeah, no problem. Thank you. Thanks.
It was nice.
Yeah, it was nice. He covered the coin change 2 problem also almost, right? Yeah.
And proof of that reversing the one.
Yeah. Because these are small things which we actually, if we think it carefully, then we can solve different problems in different ways. Yeah.
Yeah. But you have to, think it. Yeah. Okay, let me stop sharing.
Okay, so it's 9:42. I think we can go with the fourth problem, right?
Yeah.
Right.
Yeah, I think it's very simple, not it won't take much more time. Let's do that. Let me share my OneNote. Okay. So this is a problem from Geeks for Geeks. It is about maximum product when cutting a rope. So what the problem statement says, you are given a rope of length n meters. Cut the rope in different parts of integer length. Okay, so this is important. Integer length. So whenever we are given an n meters, so we can only cut the minimum amount, it will be 1 meter. Okay, and we will cut in such a way that we maximize the product of its length of all parts. And you must make at least one cut. Yeah, that is for sure. Because if you are given two, you can make one cut, right? And then actually the answer will be only one. And yeah, that is what it's trying to say. So if these are the examples, if you have n equal to, the answer will be 1. The reason is you can actually cut it into 1 into 1. And if it is 3, you can cut into 1 into 2 and the value will be 2. So if you cut for 4, it will be 2 into 2 and the value will be 4. Similarly for 5 it will be 6, but it slightly becomes more interesting when we go for n equals 10. So in that case, n equals 10, if you see that this will be the maximum. So you can actually have 3. If I would have done like something for case 10, for n is equal to 10, so it would be like, suppose if I say 3 into 7, right? So it would have given me 21 only, right? But if I actually would have resolved this 7, right? This again into broken down into different sub problems, you can say. So that will actually lead to something like 3 into 7, and then again, maybe I say 3 into 2, right? So that will be 18. Oh, 3 into 4, I'm sorry. 3 into 4, then that would be 27, right? So this is what actually happens, right? Whenever it comes to our mind, so like if we have to do such problem, so what usually comes, like I have 5, okay? So if I break this number in a such a way that it is closer to the midpoint, right? So then you think, now if I have say 5 divided by 2, and then the value will be something like 2.5, but the integer value will be 2, right? So if I say I break this around 2 into 3, so this will be my max value, correct? So that is usually we think of, and that is also true like if we have for certain numbers. But if we go for a number like 10, so in that case, if I would say like, okay, if I break it around 5 and 5, it should give me the max value, right? But that doesn't happen if we actually break down into further sub problems, like in this case, right?
Yeah.
So that is something very different about breaking it into more number of compound sub problems and finding in the most maximum value and returning it back, right? Or else it would have been a very straightforward, given 1 to n, always start with 1 and take its complement. In this case it is 9, right? So now this would be one combination, then you go with 2 and then subtract with this, the complement of it is 8, and similarly so on and so forth, right? But in that case you won't get the most maximum. So the most maximum you will get when you actually start with any number, like if you have n, if I start with I, and then I multiply that and subtract from our I, okay? But then if I consider this one to be another sub problem, and I keep on going recursively to find the most maximum value, right? Then that will give me my maximum results. Okay, so that is what the whole problem statement talks about. And also the problem is, so if we just consider that maybe something like a max product as a function, and we just pass in the value as n, so our recurrence relationship would be something like max of I say like if I'm just using this I, so I into n minus I, this will be one way, which I'm doing for certain number of numbers which are lesser than 5 or lesser than 6, I think, or lesser than 7 also. That is one maximum number, or else I can actually still say this one, and then you can use this recursive function again. Okay, this should be n minus I, right? So I just do use this again, and n minus I, if I just pass on to my recursive function, okay, and then I say this I, the I value actually will be from I, sorry, this goes back to capital. I don't know why it goes back to capital. So I value will be from starting from 1, then 2, and then all the way to n, right? So like this. So if I have this value, so this will be my recursive relationship. Yeah. Sorry, go ahead.
It should be n minus 1 only, right? I, because then only you can make two splits. If you take n only, then it will be one split on, right?
Where are you saying n minus 1?
You are saying I will go from 1 to n, right? If you take the n means entire string you are taking, so you can't make two split.
Okay. Oh, yeah. You are right. So in that case, yeah, it will be 0, and then 0, the value will be 0. But anyway, even if I do that, the max value will return the max always. Yeah. But yeah, to be safer on the optimization, why to overshoot, right? Yeah, that makes sense. You can actually prevent that because minor optimizations are also important in some cases. Absolutely. So this is the basic recursion relationship, right? So if you look at it, you can do the general way, keep on splitting it, okay, based on the index, or just go and divide it into further subproblem and then find whatever is the maximum out of these two values. But if you see, it actually keeps on going side by side with this normal constant values with the subproblem values, right? And then it goes in a recursion tree. And if I just draw out a recursion tree, actually I copied it from Geeks for Geeks, just to show it and make best utilization of all our time. So if I take a max product of say 5, and if you see the recursion tree, so it will go to 4, 3, 2, 1. Okay, because if I always subtract 1 first, so that will be 4 remaining, and then I can subtract 2, which will go to MP3, and then 2 and 1. And similarly, when I'm on 4, again I have another level of recursion values for 3, 2, 1, and so on and so forth. So there is a lot of repeatability, and then we have a overlapping subproblem, right? So this we can solve using a DP, top-down approach. Okay.
Looks like kind of MC on like different combinations of bracket weight checking, right?
Well, it won't be the MCM way. I'm not sure, but yeah, MCM way. Whenever you say I visualize only that 2D matrix with starting from the diagonal, right? Maybe that is the way I think. Maybe, but yeah, it depends on the way you think. So it might be relevant the way you're thinking also. But this looks more simpler. This problem is absolutely the way it is said here. Other than that, there is nothing. If you just implement this recursion relationship, okay, and take care of the base cases, everything works fine. It is as simple as that.
Yeah, what would be the best case? So best case when n would be equal, we don't want n to be 0, right? So n will equal 1.
Okay, so the base case, so if it is less than or equal to 0, it will be 0, right? But if it is less than or equal to, or even if it is equal to 1, it will be 1 because you'll have to return the value 1.
Mm-hmm.
Or then you can even look for something like a value 2 also, because you cannot further break down, because 2 usually, if you see in this base case here, it was like that's what you usually start with, right? So the maximum value is always going to be 1. So you can further optimize, saying your base case can be like, if it is lesser than or equal to 2, make it always 1. So for 1 also, it will take care of it.
Even for 3 also, 4 also.
Yeah, so
Three.
wherever, yeah, but you can do that, but somewhere you can stop that, So it's a base case, just go to the most minimum. And so these conditions, like even for the 5, so till this things are okay. But when we go for bigger numbers, then actually things start becoming different because we are actually breaking down into more different terms, right? Yeah. And that is what the thing changes. Yeah. Yeah, it's super simple considered other DP problems. Okay, so I'll just share my code over here. Okay, this was my integer break, right? Yeah. Okay. Okay, so okay, we have a similar problem in elite code also. Okay, so that the problem description was maximum product cutting row. Okay, here it is integer break, and if you look at the problem, only the name is different, and also the description. What it says, given a positive integer n, okay, break it into sum of at least 2 positive integers and maximize the product of those integers and return the maximum product you can get. Okay, so if you look at this 2, he gives you output 1, and then here the explanation says like this. Okay, so in this case also they explain about 10. Okay, 10 you can actually break down into, the output can be 36 if you break it down this way, right? And then in the note it says like you can assume that n is not less than 2. Okay, that is what the assumption is saying. It is not less than 2 and not larger than 58. So here they are restricting the scope of the problem.
Yeah.
Yeah. So this can be easily done the way I describe, So if I say, okay, if my n is less than or equal to 0, right, and then I return 0. And well, I'm trying to write it because it's very easy. So there's nothing more in this problem. So if I just return, because 2 is a special case also, he says, right? It's not less than 2. So for 2, if I return 1, okay, if I just take this 2 conditions, okay, and then if I say, okay, int max v is equal to, and because I'm going to find the max value, so I will just say initialize it to min, and then if I start with I equals 1 in this case, and I is less than or equal to n, okay, and I plus plus, okay, and then if I say my max v equals max of max v, and then there are the 2 things what I need to take care of, right? So if this max, I can actually say like this, okay, the way C++ as a way to implement. And also I think Roger pointed out that when Praveen did this similar implementation using this max function, I'm also using that now here. And oh, I'm sorry, actually I should implement this in a helper function. Sorry for that. I'll just make this a helper function. Okay.
Line number 5 also you can skip because they are telling only that if n will never be less than 2.
Yeah, but I will use this for now. Yeah, that is one way to do it here, right? So if I say helper, okay, so helper, actually I have to again pass n minus I, right? So I'm trying to follow the exact way the recurrence relationship what we established there, right? And then I can actually return my max value. Okay, I think I missed something somewhere. Max 3, right? Okay, let me actually, yeah, sorry, go ahead. What any questions on that?
No, line number 9, those 2 things I got, I into n minus I, and then for helper, I mean, next sub problems you are going.
Okay, line number
9. So max of max v you are taking, right? That int min you are initializing at line number 6.
okay.
So generally we pass two variables in the max, right? And then
in
whatever
this
result.
in this max, right? Yeah, so what I'm
And
trying to do, yeah, there is one way of C++, and I think in one of our session, Roger also mentioned C++ can use this way to find a max value. If we use this curly braces inside that, whatever number of values you pass in, so it will find a max value.
okay, n number of values.
Yeah, a number of values. So I'm just trying to take that help, no? And without memoization, this may work, yeah. So it might give PLE on some cases, right? Yeah. So if I add memoization, then it will be fine, right? So if I add something like a vector, and then if I have in here, say memo, and I'm using a memo for my n plus 1, okay, and this say minus 1, right? And then I pass here memo, okay, and here actually use this memo here, and this so vector and this memo, and then if I pass my memo inside this guy, right, and now what I have to do is I have to assign memo here, right? Memo of n
Max V.
is equal to max v, and then here I have to check if my memo is not minus 1, right? Memo of n is not equal to minus 1, then I return memo n, right? So I think if I do this, this will be my top-down approach, right? And this should go through because I tried it earlier also, yeah. So this works fine, right? So this is a very simple DP pattern, I would say, correct? It's nothing big about this, and I think we have been using this similar sort of implementation in many places. And it also has only a single helper function. We don't have combinations of more of them, and we're just comparing the max values, right? So that was the top-down approach. So you can use a bottom-up approach also, similar way, okay? And then instead of using a memo, we can use the DP for it. And if we repeat the same things, all these base cases, then it should be fine, right? I can actually share that, whatever I have it here. So that
Single array.
should be, yeah, single array should be the better way of doing it if it is this one. Yeah, I think I have, yeah. And then
No, yeah.
and the way you were saying that instead of 2 you can use it 1, right? Yeah, that should also work because I'm initializing this one, right? So instead of 2 you can, yeah, that also works fine. That should work fine. So if you look at this implementation, it is exactly the way I did for the top down also, correct?
Yeah.
Almost the same. But oh yeah, in this it will be slightly different. Okay, yeah, that's one thing, because we need to find the max value always till your I, right? So therefore you'll have to run a for loop again, starting from the very initial position, okay, to your ith value, right? So that is the one different way to implement in a bottom-up approach. And therefore, bottom-up approach for such a simple top-down approach, you know, it's not very intuitive, right? This way. Yeah, it is the right way to do it, but it doesn't come up very easily. So therefore, it is slightly tricky when we implement a bottom-up approach. Yeah, but yeah, so this is the way it is. And as you said, yeah, we can reduce these values. We can make it 1 also, right? And I think that should also work in this case. And also the previous case also it should work. Yeah, yeah, yeah. So what your observation was, correct, Shashank? Yeah.
This is also the minimize, optimize DP.
Oh yeah, okay.
Game minimize.
Yeah, but I think this is one of the most super easy problem, right? In all the DP.
Super easy was climbing stairs.
Climbing stair, well, yeah, this guy also. Yeah, climbing stair, it falls in that Fibonacci series. So we have been doing it very many times, so we know it very well, right? Yeah. And this is very easy. Like when we break down a rope, we can actually make this, you know. And then the only slightly different way of thinking is if we actually break down the rope further, what happens? And that is why the recursion comes into help. Or else the best way is just go to the mid of the rope and then find out if we can break into half, or not exactly half but equal, most equal optimum halves, you know. And then that value should be the biggest value. But if you are allowed only to make a single cut, then I think this is the only way, right? But if we are not, they are not saying that. So in this case, we are allowed to make more cuts, and that is the reason the recursion comes into picture, and therefore the DP solution. Or otherwise, the problem is super easy.
Yeah, exactly.
Yeah.
So in the helper, if we instead of make a 2 cut, we can make 1 cut. Then yeah, then maybe we can remove the I time, n minus 1. Keep thinking.
Oh
right?
no. So in that case, we can only remove this one. So if we remove I minus n minus 1, because we are allowed to make only 1 cut. So this is the only way we can do. Because if we use recursion, so we are actually allowing it to make more cuts. Because further down the recursion tree, and if we have more scope of cutting it in the integer value, so we can cut. So then we obstruct this whole recursion, then it is a normal, very simple for loop problem. It is not even going to fall in any of the recursion problems. So that is a slight difference. Yeah. Therefore, I said it's a very super easy problem. If someone gets this, then it's the most best thing in an interview, I would say, right?
Or still need to think. It's not like because the way you explain it make it easy. But when first look at it, it would be like if you try, because the way first I look at it, I say, okay, just take the median, take the middle, like you say, like if it 10, take the median 5 times 5, that's what I think.
Yeah. Oh yeah, if you go that route, yes, absolutely, because that will come initially, but then if because this will help, writing down the test case will surely help in that case. So we'll have to always write some test cases, but in this test case we'll have to remember for this special test case, which is 10.
Yeah.
So when we come to 10, then things are slightly different, because before 10 everything will be almost the same.
Yeah.
Yeah. So you'll have to come with a test case, and then you'll have to run through all of the. I can also show the how it looks like when actually. Okay, this is the Excel sheet, and this was for the 10 I was running. Oh, I think even if you for 9, if we have 4 into for 9 also it doesn't work, it seems, right? So 4 also doesn't work. I think from 7. So 3 and 4, 12. So from 7 it is fine, till 7 it is fine. From 8, 9, 10 it uses a recursion function. So 8 is important.
Well, then we can make a best case from 1 to 7.
Yeah, that was happens. If we have a test case only till 1 to 7, we'll go, okay, this is something very simple problem, and we'll just solve it using a for loop, right? So therefore the test case becomes handy. Yeah. So in that case, yeah, what you say is, Leon, makes sense. It's not an easy problem to visualize if we have limited test cases. So we'll have to take, I think the interviewer will give us some test case of 10 or so, right? At least when we are trying to walk through how we understood the problem, with different test cases. So he might say, okay, now what about 10? How we will to do that? Because he will always push us, because it's not so easy to come up with a problem. So there we will need any help from an interviewer, right?
Yeah.
If you have never seen a problem like that, or else I would never come up with this way also, right?
Yeah, exactly.
Yeah. So what you are saying is right. In that case, not that easy when we are just given this problem statement and say, okay, we don't even know whether it's a greedy or whether it is a DP problem, correct? So then how do we come over with? So test case will help, and then he will have to help. If it doesn't help, then I think it's difficult. But usually they will surely help, right? At
Yeah.
least,
Yeah, right. Yeah.
that is what a reasonable expectations from all of us, right? Yeah. Okay. Yeah,
Yeah,
that's good.
thanks.
Yeah, thank you. So I'll just stop the
Thank you,
recording.
guys.